one. Okay, so the question was just posed, how many more sections do we have? So we have, like pulling up my notes here, we have section 5.4 to do today. I'm going to try to get a majority of the notes done today so that tomorrow, I know I will still have to do like 1 or 2 problems tomorrow, but a majority of tomorrow will be a work day. It's kind of like a day and a half lesson, not necessarily a 2-day lesson. And then we will take our quiz, take our test. So we will be doing, so we did 5.1, and we did 4.9 and 5.1, and then we did a quiz. And then we did 5.2 and 5.3 and did a quiz. And then we will do 5.4 and then have a test over all of that. Okay? That will be next Thursday, Friday? Right. That just popped in my head. I think it's next Wednesday, Thursday. Yeah. Next Wednesday, Thursday. Because honestly, if we get this done, most of it today, tomorrow's a work day, that means we have Monday, Tuesday to review. Okay. Monday, Tuesday review, test, Wednesday, Thursday. And then we are going to do, and this is kind of weird. After that, we do section 5.5 and 6.1. That's it. So we do section 5.5, and it looks like, again, I've titled 5.5 partner quiz. I have no idea what that looks like. But 5.5, I won't pull it up right now. 5.5 partner quiz, and then we have a 5.5 and 6.1 test.
Wait, I thought that was a test. Or is that a quiz? Over all of that.
Yeah, there are 2 tests for this 9 weeks. This first one that we will have by the end of next week.
Is that the partner one?
No. This is only going from 4.9 to 5.4.
Oh, 5.5 that.
Yeah, and then we do change color for emphasis. 5.5, and then a quiz. 6.1, and then our second test for the 9 weeks. And then we review for our exam.
We got 3 homeworks left.
It's not necessarily tough. It's just different. It's just yeah. A lot of the stuff that we will do from here on out is not necessarily more difficult than one another. It's just like learning new things that we can tell about this. Like, and that kind of leads me right into today's lesson, the indefinite integral and the net change theorem. Today is going to be more of the indefinite integral. Tomorrow is going to be more of the net change theorem. But basically, thinking about it in terms of what we learned before, we had been talking about definite integrals, right? Definite integrals. And so what is the difference between a definite integral and an indefinite integral? Well, a definite integral gives you boundaries, and an indefinite integral does not. An indefinite integral leaves it open so that you can really put the boundaries wherever you'd like them. Both parts of the fundamental theorem establish connections between antiderivatives and definite integrals. And definite integrals tie right in hand with the antiderivative. Now, that is going to be the exact same thing that we're going to use for an indefinite integral as a definite integral, using that antiderivative. Part 1 says that if f is continuous, then the integral is an antiderivative of f. That's what part 1 says. And then part 2 says that you can evaluate f of b minus f of a. Okay, so what if we take away that piece of knowing b and a? What if we take away that piece of knowing that it's a definite integral? We need a convenient notation for antiderivatives that makes them easy to work with. So basically, what we have here is an indefinite integral, and this is the notation that we can use. Now, honestly, it's like the same thing that we learned in section 5.3 about the definite integral, knowing that the antiderivative is really equivalent to the integral. We had said, okay, it's got to be having 2 endpoints, and then you can actually evaluate what it is. For a definite integral, the end result was a number, an actual area. For an indefinite integral, the end result is a function. Okay? So in a definite integral, the output, like the answer blank, is a number, an area, For an indefinite integral, the answer blank is an equation. The answer blank is an entire function. The answer blank is an equation that I could use to find the area given any 2 points. Okay? That's really what the end result is going to be today. Give me an equation that I could use at any point in time to find, okay, if I want to go from 1 to 3, I know how to do it really easily. If I go from 0 to 4, I know how to do it really easily. If I go from 7 to 10, I know how to do it really easily because I can evaluate pretty quickly. So basically, this is the notation that we can use. Notice that there are no endpoints on our integral now, right? Our integral now has no endpoints. It's called an indefinite integral. So we have this indefinite integral. The integral of f of x dx is equal to f of x. And remember that capital F of x is meaning the antiderivative, right? And we can say that if we find the derivative of capital F of x, it will get me small f of x, right? Just like this. The integral of x squared dx is x to the third over 3 plus c. Now notice this plus c. That plus c is coming back again. Now let's think about it. Why did it go away? Why did that plus c go away? I said you didn't need to worry about it, but why didn't we need to worry about it? Well, think about it this way. Let me move this down a little bit. Let me show you what I mean here. If I were to add in that plus c every time we do a definite integral, say from a to b, whatever it may be. So a to b. Oh yeah. Yeah, f of b minus f of a. And it was that x squared, right? What if our f of x was x squared? Well, that would mean my antiderivative is x to the third over 3. And I said, forget about the plus c. Well, what if we didn't forget about the plus c? What if we said, okay, no, we needed that. What would this look like when we evaluated it? This would be b to the third over 3 plus c minus a to the third over 3 plus c. What's going to happen there? That's b to the third over 3 plus c minus a to the third over 3 minus c. That's why we could forget about it, because it was always going to cancel it out. So I said forget about it. It's not even needing to worry about it because I knew it was always going to cancel out. Now, when we talk about having an antiderivative, an indefinite integral, and we have to use the antiderivative, now we have to bring that plus c back in, okay? Because if we're truly creating the function, we have to think about that antiderivative being that generic antiderivative, that plus c antiderivative. Okay, now I did add this into the notes that you could print out if you like. This is just kind of like a cheat sheet of all different types of integrals and how they relate to their original and how they evaluate. We're going to use a lot of the properties here, but it might be a good idea to have these trig ones there for you on your homework when you do your homework, just to have it there for you, so that if you needed it, you can quickly reference it. But a couple things here that I wanted to point out: if you have a constant within an integral, you can pull that constant out of the integral, c times f of x. If you've got a sum of two functions and you're taking the integral of that, you can take the integral of them separately, which we'll use here in a second. This is our power rule where we kick it up one and then divide. This is if x is -1, right? If the power is -1, that'd be 1 over x. Remember, that's the ln. E to the x plus c, right? E to the x is e to the x. So basically, these is just a table of indefinite integrals that you could quickly reference on how to find the antiderivative at any given time. Okay, we used them as antiderivatives when we were talking about them in section 4.9. Now we're changing the terminology, calling them indefinite integrals. It's really kind of the same thing. When I say indefinite integral, you think antiderivative. Same thing with definite integral. When I say integral, you should think antiderivative. Okay. All right. So let's talk about it here. Find the general indefinite integral. So basically saying, create for me an equation that I could use to find the area given any 2 points along that line, along that curve, which is kind of like the same thing that we did with derivatives, right? I said, give me an equation that I could use to find the slope at any given point. Give me an equation that I could use to find the area under the curve at any given time. So basically what I'm asking you to do is just find the antiderivative. Find the antiderivative. Now remember, what I can do here is this. I can separate this minus the integral of 2 secant squared x. right? Because if you've got a sum or difference of integrals, you can take the integral of each one. Well, we know how to do this one. This one's pretty easy. 10x to the 5th over 5. And then we take this minus. We got 2 secant squared x. Hopefully there's a secant squared. Is there a secant squared? Yep, right here. 2 secant squared x. Now, notice that there is a secant squared, right? So I could bring that 2 out. Like if I really wanted to, I could say minus 2 integral of secant squared x. Which essentially, okay, so bring this down, that's an x to the 5th, minus 2, 2x to the 5th, minus 2, and now go back. Secant squared was tangent x plus c. 2 tangent x plus c. And honestly, I should have done that, right? Because it's 2 times that whole integral. That plus c takes care of both pieces there, finding the integral. Yeah?
What is the 10x to the 5th over 5 and it's on plus c?
No, it's the same constant. Because we're only talking about one function. But if you separated it, you can use the same constant at each one. Yeah. You don't have to say like plus c plus d. It's not like that. So 2x to the 5th minus 2 tangent x plus 2c. Questions about that? And now I can say at any given point, what we can find the area given any 2 endpoints. I want to find it from -2 to 2? Sure. Plug in -2, subtract it from +2. Take a look at this one. Cosine theta over sine squared theta, d theta. Now, I believe, that's what I'm getting on my notes, I believe this one requires a little bit of simplification before we start. Yeah. See, is there a division rule or anything that we can use like that? No, there's nothing where I can like find the antiderivative of a division, of a fraction. I don't have anything like that. But what I can do is find antiderivatives of regular trig functions. So maybe I can reduce it down so that this is a regular trig function. Here's what I mean. This is going to be equivalent to cosine theta over sine theta times 1 over sine theta d theta. Okay, what did I do there? I just kind of removed a sign from the bottom. Because cosine over sine times 1 over sine is really cosine over sine squared. Okay, what is cosine over sine? Cotangent, yeah. So this is cotangent theta. What's 1 over sine? Cosecant. Cotangent cosecant d theta. Is there a cotangent cosecant? Oh, I must have ripped it out of my notes. I was looking for my cheat sheet. I must have ripped it out of here. I guess I got to go back over here. Cotangent cosecant. I'm looking for a cotangent cosecant. Bingo. Right? Because that's really the same thing, right? Cosecant cotangent is the same thing as cotangent cosecant. So it's negative cosecant x plus c. Negative cosecant x plus c. So negative cosecant theta plus c. And again, given any theta, given any 2 points, A and B, I can find the area under the curve using that equation. which is essentially just the antiderivative. And I guys, we're not really learning anything new here. We're just kind of like shifting the terminology to say, oh, okay, remember antiderivatives are the same thing as integrals, so let's just keep calling it that. All right, now I'm making it a definite integral. This is something that we definitely could have done on yesterday's quiz. Yeah. The rest of the next couple examples, example 3, example 4, and example 5, are all in example 6? No. Examples 3, 4, and 5 are all definite integrals now. So just more of the same. More of the same. Just different types of functions now. But this is kind of an easier one, isn't it? So this is x to the 4th over 4 minus 6x squared over 2. Right? From 0 to 3. Why am I not adding in my plus c? Because it's a definite, right? And it would cancel out. It would cancel out. If I asked for the indefinite, I have to say the plus c because I'm asking for the function. If I say the definite, I don't need it because it's going to go away in the end anyway. See, these numbers here, having numbers on the integral, is telling the reader that the output, the final answer, should be an area. Did that come from the other room or come from up? So we got x to the 4th over 4 minus 3x squared from 0 to 3. Okay, let's plug it in. That's 3 to the 4th over 4 minus 3 times 3 squared minus, plugging in 0. Well, 0 to the 4th over 4 minus 3 times 0 squared. Well, that's all going to be 0, isn't it? So this is 3 to the 4th divided by 4 minus 3 times 3 squared. Negative 6.75 minus 0, so negative 6.75. Okay, let's try another one, shall we? Any questions on that one before we move on? We're not going to interpret the results in terms of areas. We're just going to find it. Find that definite integral. So going from 0 to 2 of this weird function. Now, remember what I can do here. I can break this apart. Like something weird is happening in the end here, isn't it? Right? So what I can do is break it apart to make it not so weird. So 0 to 2 of 2x cubed minus 6x dx. I guess I should put those dx's in there. Plus, now, I've got this funky thing, but taking a look here, do I have anything that looks like that? Take a look at here. Oh, no, the next one. I've got an x squared plus 1 on the bottom. Do I have something with an x squared plus 1 on the bottom? Yes. Inverse tangent. Okay? But what does it have on the top? A 1. So maybe we can manipulate this to have a 1 on the top. Oh, pull the 3 out. Okay. So this is going to be 2x to the 4th over 4 minus 6x squared over 2. And now I'm going to go right in here and say this. Plus 3. Hold on. Yeah. Hold on a second. Go ahead and finish it. You should know. good, Camille? Okay. Sorry, and we're back. 3 inverse tangent, right here is where I'm looking. 3 inverse tangent of x plus c. 3 inverse tangent of x plus c. But there's no c, right? Because it's a definite. And I can go now all the way to the end and say from 0 to 2. Because just like I can break it apart, I can put it back together. Question. All right, let's reduce that though. 2 over 4 is 1/2 or 0.5. And we plug in 2 and then we plug in 0, right? So we've got 2 to the 4th, or 1/2, 0.5 times 2 to the 4th minus 3 times 2 squared plus 3 times inverse tangent of 2. That's all plugging in 2 minus, okay, we got 0.5 times 0 to the 4th, that's all 0. Minus 3 times 0 squared, but that's 0. Plus 3 times inverse tangent of 0. Okay, let's plug it in. We have 0.5 times 2 to the 4th minus 3 times 2 squared, which is 4, plus 3 times inverse tangent of 2. Negative 0.68. Now, I don't know if this other one's going to come out all the way to be 0. I know these first 2 terms of it are going to be 0, so let's just plug in the very last one. 3 inverse tangent 0. Okay, that's 0 as well. So I guess there's my answer. Negative 0.68. You know, if I were to show you this problem at the beginning of the year and say we'll be able to do this by the end of the year, you'd be like, no way. Like, look how, if you just feel smart, okay? Just feel smart for a minute when you're doing your homeworks. All right, let's take a look at this one. Like, we are up in thin air up here. There's like not many people that can do all of this stuff. We can. Well, we're learning. All right, evaluate from 1 to 9 of 2t squared plus t squared times t to the times the square root of t minus 1 dt. Now, this looks all big and bad, and it's like, oh my gosh, what the heck am I going to do to this thing? But simplify it first. Remember, try to make it look like a polynomial first. Then you can start to evaluate finding the antiderivative. All right, let's do it. Because here, I'm going to evaluate this. 2t squared over t squared plus t squared radical t over t squared minus 1 over t squared. Right? I'm going to break that t squared. I'm going to break this fraction, break this rational up into all of those little pieces. So that's going to end with, okay, that's going to cancel. So just a straight up 2 plus square root of t minus 1 over t squared. Because that's going to cancel as well here. Now, let's put it back in the integral form. So that's going to be from 1 to 9 of 2 plus, now I'm going to make this a fraction power. T to the 1/2 minus, and then a negative power. T to the negative 2. So always go to try to make fraction powers rather than radicals and negative exponents rather than fractions. Okay, so now let's find the antiderivative. So this is 2t plus, 2t over 2. No, over 1, sorry. Sorry. Plus t to the 1.5 over 1.5 minus, t to the -1 over -1. That's not an ln. That's not an ln. I don't need to worry about that. Going from 1 to 9. Okay, which is equivalent to saying we got 2t plus, I don't really know why I'm writing this, 1.5 over 1.5, all to say a plus t to the -1. From 1 to 9. And now we evaluate. So this is 2 times 9 plus 9 to the 1.5 over 1.5 plus 9 to the -1. And then I'm going to subtract away 1 plugged in. 2 times 1 plus 1 to the 1.5 over 1.5 plus 1 to the -1. Yes, sir. What's that? Oh, thank you. You need to go? Okay, we plug in. We plug in. Let's take a look. 2 times 9 plus, I've got 9 to the 1.5 divided by 1.5. I don't know if that's going to come out nice. Hold on a second. This is going to be 18. 2 times 9 is 18. Plus, I'm going to go 9 to the 1.5 in parentheses divided by 1.5 plus 1/9. Because that's 9 to the -1. 36.1. Repeating. 36 and 1/9, if you will. Let's plug in let's plug in 1. 2 times 1, or just 2, plus, and then we have 1 to the 1.5. 1 to the anything is 1. Divided by 1.5. Plus 1 to the -1st. Well, 1 to the -1st is 1 over 1. Plus 1. So 3.6 repeating. So we have 36.1 minus 3.6. 32.5. I think it's probably 32.4 repeating, but questions about that? No? Hey, I've still got 15 minutes. Can I just finish these notes? Is that okay? That way you can have all day tomorrow to work. All right, taking a look here. This is what's called the Net Change Theorem. Guys, honestly, it's basically just a word problem version of what we've been doing. Remember all of those things that we did in chapter 3 where it was like, find the rate of change, like how fast is the water filling up the tank? Or how fast is the balloon blowing up? You can do all of those things just in reverse, right? What does that mean? That means that, like, and I've got some, it gives us some applications. So I just want to kind of talk through some. No. There's somebody at my door. Oh, there's this cop that parks right outside my house to watch the stop sign right by the end of our road. He's sitting there. All right, sorry, back to this. If V of t is the volume of water in a reservoir at time t, then it's V prime of t is the rate at which the water flows, right? the rate at which it's increasing or decreasing. That would be the derivative, right? So if I flipped it on its head, if I flipped it around, I could say that the integral of any time, right? If I had endpoints of time and I wanted to find the integral, that is actually going to be the change in the amount of water that's in the reservoir, right? Not how fast it's moving, because that's the derivative, not how fast it's flowing in or out, but the actual amount of net change of water from one time to the next. If C of t is the concentration of a product of the product of a chemical reaction at a time t, then the rate of reaction is the derivative, right? The rate is the derivative. So what is the integral then? The integral is the change in the concentration from any two time periods. The actual amount of the concentration, the change in the concentration, that is the actual what's evaluated to be the integral. If the mass of a rod is measured from left endpoint to right endpoint, then the density is the derivative. Okay, so the integral is the mass of the segment of the rod between A and B. If the rate of growth of population, this one, I don't understand that one, maybe you science people do. This one I understand a little bit more. If the rate of growth of population is a certain function, right? I know the population is growing or decreasing at a certain rate. Then I know that the integral is equivalent to the net change in population. See, that makes sense in my mind. If you know that the derivative is equal to the actual change, like the instantaneous, how fast or slow is the population growing or decreasing, then that must mean that the integral is equal to the amount of net change of actual people within that city. Okay, and then the last example here that they give us a lot more. If C of x is the cost of producing x units of a commodity, then the marginal cost is the derivative. Okay, if the marginal cost is the derivative, then the integral is equal to the increase in cost when the product is increased from x units to, at any two given times. Okay, that is like what I don't do econ or whatever. But here is what we will be focusing on. Okay, we've talked at great length in this class about position, velocity, and acceleration, right? We've talked about that a lot. That's like the main, our go-to example when we talk about derivatives and antiderivatives, right? That's our go-to. Velocity, acceleration, and position, right? So that's really what we're going to be sticking with. If an object moves along a straight line path with position function, then its velocity is equal to the derivative, right? Velocity is the derivative of position. We've learned that long ago. So that must mean that the integral of velocity, the definite integral of velocity at any two given times, is equivalent to the net change in position. That's really what we will be using here. Now, what does it mean? What does net change in position mean? That means, what is its displacement? How far is it away from our starting value at time 1? Okay, let me say that again. If an object moves along a straight line path with position function, s of t, then if the derivative of position is velocity, then the integral of velocity is the net change in position. The net change in position, which in other words is displacement. Okay, in other words, that's displacement. So I can actually calculate displacement, and I can also calculate total distance traveled. What I need to do, though, when I calculate total distance traveled, is calculate if I have changed directions. If my velocity has turned from a negative to a positive, basically. Okay? Because remember, the difference between displacement and distance is displacement, I'm just thinking about where do I end up in relation to my starting position. And distance is how much have I actually moved. Okay, how much have I actually moved? So let's take a look at this one problem here at the end. Perfect, 10 minutes to do. A particle moves along a path so that its velocity, a particle moves along a line so that its velocity at time t is v of t is equal to t squared minus t minus 6. So I'm given the velocity function. and we're told that it's measured in meters per second. What I would like to do is first find the displacement, that's A, and then second find the distance. I need to find the displacement, and then I need to find the distance. Now, total displacement is strictly equivalent to the integral. Right? That really is just my displacement. Total displacement is really just equal to the definite integral from one time to the next. And we can calculate that because we're told what v of t is. So that's equivalent to equivalent to the integral from 1 to 4 of t squared minus t minus 6 dt. Okay, well that's not too bad. So that is t to the third over 3 minus t squared over 2 minus 6t from 1 to 4. The antiderivative, and then plugging in f of b minus f of a. The net change of position, net change of displacement. So that would mean it's 4 to the third. Whoa, where are you going? 4 to the third over 3 minus 4 squared over 2 minus 6 times 4. My end point, my f of b, minus my whole f of a. 1 to the third over 3 minus 1 squared over 2 minus 6 times 1. That's going to be my total displacement. So let's run it. 4 to the third divided by 3 minus, okay, that's 4 squared is 16 over 2 is 8 minus 24. Negative 10.6 repeating. Minus, okay, so this is really just 1/3 minus 1/2 minus 6, right? 1/3 minus 1/2 minus 6. Negative 6.16 repeating. Okay, let's take negative 10.6 minus a negative 6.16. Negative 4.44. That is total displacement. So from time 1 to 4, I am now, at the end of 4 seconds, I am now in a negative direction, 4.44 meters. Right? Net displacement is 4.44 meters in the negative direction. That's what that negative means. So that must mean, maybe I'm moving backward and forward, right? Maybe I am changing directions somewhere in there. Now, if I change direction somewhere in there, that must mean that at any given time, my velocity must switch from negative to positive, right? I must be moving in a negative direction to a positive direction. Okay, so now, here's what I have to do for part B. Okay, for part B, what I have to do is figure out when that could possibly happen. Meaning, when is my velocity 0? Because when my velocity is 0, that must mean I'm at the point where I've stopped and tried to go back to the other direction, right? At any time where my velocity is 0, that's when a change in direction has occurred. All right, well, that's factorable. So t minus 3, t plus 2. So t equals 3, t equals negative 2. Now, what range of time am I focused on? 1 to 4. So do I even need to worry about negative 2? I mean, honestly, negative 2 seconds is kind of weird to say anyway, but I'm only worried about this time 3 here. So what I'm going to do is calculate what's going on from 1 to 3, and then calculate from 3 to 4. I'm going to calculate 1 to 3, and I can write this in, of v of t dt, and then calculate 3 to 4 v of t dt. I mean, I can run the numbers and see what's going to give me, I know there's a change of direction at 3, and I could run the numbers and see, like, okay, which one's moving in a negative direction? I can do that really by the increase-decrease test, right? I can just draw a quick number line and see, plugging it into the velocity to see where it's negative, where it's positive. But I don't even really need to do that because I know one of these is going to come out negative, right? And what do I do to find the total distance traveled? Just make it the absolute value. Just turn it positive, right? Because I'm only worried about how much distance have I fully traveled within this given time period. So let's run 1 to 3. Well, I've already found my antiderivative. Wasn't it t to the third over 3 minus t squared over 2 minus 6t? I just got to run it twice. So from 1 to 3, right? From 1 to 3 of, and this is, again, t to the third over 3 minus t squared over 2 minus 6t dt. Actually, no, I'm sorry. My notation is wrong here. Here. Because we've already taken the antiderivative. So let's run the numbers. Let's plug in 3. 3 to the third over 3. Is that going to give me 27 over 3? 3 to the third. Do I need to do parentheses? No, I don't. Okay. So it's 9 minus 3 squared is 9 over 2 minus 6 times 3. Negative 13 and a half minus, and then I got to plug in 1. Oh, that's that 1/3 minus 1/2 minus 6. Yeah, we ran that number already, right? Negative 6.16. Okay, so looking at this one, negative 13.5 minus a negative 6.16. So that's my negative distance, negative 7.34. So what am I going to do to that? Just turn it positive, right? Because I'm moving in a negative direction, but I really want to know how much distance has been traveled. 7.34 meters. And now I just have to evaluate this exact same thing. T to the third over 3 minus t squared over 2 minus 6t from 3 to 4. Okay, so plugging in 4, this is 4 to the third divided by 3 minus 4 squared divided by 2 minus 6 times 4. Negative, that doesn't seem right. Yeah, no, I guess it is. Negative 10 point, yeah, this is right. Negative 10.6 repeating. And haven't I already evaluated when I plug in at 3? It's that negative 13.5. So negative 10.6 minus a negative 13.5. It's going to come out positive now. That's what I was worried about. 2.9, right? Yeah, 2.9. So 2.9 meters plus 7.34 meters gets us a grand total of 10.24 meters. That's the total distance traveled. Not displacement, but total distance traveled. I've moved in the positive and negative directions. Total distance traveled is 10.24 meters. Sorry, that was a lot of notes today, but we don't have to do any notes tomorrow.